And this, okay, so now that the recording is going, we've got 2 chlorine positions. So far, no response about why one of them might be better for the nucleophile to attack than the other. So let's imagine if it attacks here, we get this position for the lone pair. And that lone pair across a 3-atom system, you guys remember this idea of the 3-atom system, right? A pi bond across 2 atoms and either a lone pair or a charge, or sometimes both. So 1, 2, 3, my lone pair goes in, my lone pair comes out. I get another resonance form. Now I have that negative charge on a carbon. Another carbon. One more resonance form, lone pair in, lone pair out. Place my lone pair on the last carbon in the ring. A little messy, sorry. Why did the lone pair not go into the electron withdrawing groups? Isn't that the point of an electron withdrawing group, is to withdraw electrons? Can you name why it didn't?
It's not ortho or para.
What was not ortho or para?
The leaving group. Oh wait, no, the electron withdrawing group compared to the chlorine.
Good, because ortho-para is a relational term. You have to relate 2 things. So it's good that you added both. Because the leaving chlorine is not ortho or para to the electron withdrawing groups. Why didn't you just say that earlier? We wouldn't have had to draw it all out.
Compared to the top chlorine, isn't it?
Isn't it what?
Ortho?
It's ortho to the top chlorine, but is the top chlorine an electron withdrawing group? Does it have a pi bond that can pull electrons out away from the ring?
No, but...
What it has is a lone pair that it could actually push towards the ring. It has a dipole, yeah? It's pulling electrons towards itself, but not accepting electrons, yeah? So that's all of our resonance forms, and the last step of this mechanism, if you remember, is elimination. The lone pair reforms a pi bond and kicks off the leaving group chlorine. What were you going to say, Jordan?
But compared to the top chlorine, both of them work.
Oh, well, yeah. This is what we call pushable.
Okay.
We just pushed an arrow pushing mechanism for it, weren't you? But how much energy did this take? On a semi-quantitative energy diagram, this is our reaction coordinate. Do you guys know, have you seen this term before? Reaction coordinate. Do you know what it means? It's less about physical space and more about conceptually where along the mechanism are you. It's kind of like the journey through college. It has its ups and downs and easy points and its hard points. And it's not so much about physically where are you on campus, it's more about conceptually where are you in your degree path. That's the reaction coordinate. It's not a physical location, it's a conceptual idea about where the energy is. Okay, so we know that this can happen. And we know that it takes a lot of energy to break aromaticity. Aromaticity is a stabilizing force, so to break aromaticity takes a lot of energy. We have a resonance stabilized intermediate, that's up here, and then we reform aromaticity. you remember what we call that resonance stabilized intermediate? We call it the sigma complex. And I don't think that's the first time I've started calling it the sigma-sigma. Sigma complex. Okay, if the nucleophile attacks at the top, with ortho-para electron withdrawing groups, which is different than that first chlorine because the electron withdrawing groups were not ortho-para. And the relationship to each other in the ring makes a difference in the resonance form. Here's my nucleophile. My nucleophile attacks at the chlorine position, and it can break this pi bond right onto this carbon. Do you want to see that resonance form? I don't particularly care for it because carbon holding a negative charge doesn't do a lot. But it's not wrong to show it, and if you do show it, you create a 3-atom system. So I'm just going to push right in to that next system. I create a resonance form. Nice. Because the electron withdrawing group was ortho, the nucleophile pushed electrons straight into the electron withdrawing group. Are you okay with the fact that we skipped over a resonance form? Good, because no resonance form exists anyways. So we can draw it and then take the time to draw another one, or we can just push right to it. Do what you need to do. Practice pushing as many resonance forms as you need to until it becomes easier to notice something like this. All right, well, I could have pushed directly to the other electron withdrawing group as well, but I didn't. So now I'm going to push to the other electron withdrawing group from within this resonance form. So the CO double bond reforms. Remember, a bond breaks to the more electronegative atom, and a bond forms from the more electronegative atom. It's always the atom that controls the electrons that controls the electrons. Then this pi bond comes back into the ring. This pi bond leaves the ring, and this pi bond goes to the oxygen. I love this cascade. Good morning. This cascade of electron arrows as the electrons flow to the other electron withdrawing group. How many resonance forms did I skip over? Well, I had already skipped over this one, but then I also skipped over a resonance form where the lone pair was held on this carbon. And I skipped over that because I'd rather show a resonance form where oxygen holds the electrons. Not that this resonance form doesn't exist, it's just not a major resonance form.
Could you just, like, do you have to show, actually, I kind of answered my own question.
Let's hear it though,
Okay.
for the people that maybe are thinking the same
Okay.
question.
Can you, because I was thinking you could just push the electrons back to the leaving group, so that would leave first, but I think you want us to show all of them at once.
Correct. You could show one resonance form forming, whether it's held on a carbon, an oxygen, this carbon. You could show one resonance form and then show the elimination step. But what I'm asking for are all major resonance forms in the intermediate. Good question. Okay, well, this is my last major resonance form because I have no other electron withdrawing groups. So I'm going to push from this resonance form to the elimination. My pi bond reforms, my pi bond moves into the ring, my other pi bond shifts, and that kicks off my leaving group. It's a lot of arrows, and it's all just resonance. So if that's too many arrows for you, then draw more structures. That's the compromise you get. You can either have less structures but more arrows, or more structures with fewer arrows each. All right, now the question, did this take less energy to accomplish than our first one? Well, in blue, the nucleophile had to break aromaticity and then stabilize a charge on all carbons across 3 resonance forms. But in red, our sigma complex stabilized the negative charge on oxygens and had a total of 5 resonance forms. 3 where carbons held them, which were minor resonance forms, and then these extra 2 where the oxygens held them, which are major resonance forms. And we know that resonance is a stabilizing force. So it takes less energy. And to be honest, I don't think that this really does the difference in energy justice. Three resonance forms in blue, 5 resonance forms in red. So as you start giving energy to this system, you give energy to the molecules, you get them moving around and running into each other. Eventually, you have enough energy to overcome the activation barrier in red, and you attack at the position that has an ortho and a para leaving group. Is it possible to attack the position in blue? Yeah. But if you get enough energy to do that, you have already had plenty of energy to do the other. So maybe you'll get it as a minor product. Generally, like less than 10%, you might say, will form that other product. So we can say our major product for this reaction, substituting the halogen with an ortho-para leaving group. Sorry, substituting the leaving group with an ortho-para electron withdrawing group. Okay. I mentioned something earlier that I kind of misspoke when I said it. I said we could substitute both of these chlorines, and I meant to say we could substitute either of these chlorines. We actually can't substitute both of them because after one of them forms, it has an electron donating group. The electron donating group is the oxygen with its lone pair that can be donated in. Different from these groups with pi bonds that pull electrons toward oxygen. The oxygen of the ether has lone pairs that can be conjugated and can be donated into the system. And electron donating groups, you know, it's really hard to say whether inhibit or prohibit is a good term. I'm going to say prohibits NAS Because inhibit makes it sound like it just increases the activation barrier. And it does. But it increases the activation barrier like this. Like it's not close. The amount of energy that would be required for the product, either product, to go through substitution again is now off the charts. It's not going to happen. Once you have an electron donating group, NAS is just not feasible. And there are some exceptions to that, of course. No rule is free of an exception. Nitrogen and oxygen donating groups prohibit. Alkyl groups, we're going to talk about this today, are considered electron donating, and they do allow NAS. And that's because they're just not a strong donator. They don't actually have lone pairs. They just have electron density that they can donate to the ring. So I want you guys to talk with each other, please, since you won't talk to me. And I want you to rank these questions on the bottom of your sheet. Does anybody need a sheet? I want you to use this idea of, Joan?
Different than last week's? Oh, yeah.
You're welcome. I want you to use this idea of electron withdrawing groups and electron donating groups and their placement relative to the leaving groups to rank them in order of reactivity to NAS. Okay? You have 5 minutes.
Did you get the opening on video?
Kind of.
Okay.
I don't know, my system's being funky today. It says it's recording, and it says that the microphone is working.
So we'll see.
But earlier, I started recording, and it wouldn't turn off. So I restarted my computer and my phone, and it turned on again with the same recording going. But no time recorded. So I'm hoping that when this is done, it saves.
Okay.
Because I'll be honest, this is the best I've ever done presenting this topic ever in my 3 years of teaching OChem 2. I've never taught EAS and NAS this well, and I'm excited to see how it goes. And I really want this video to be saved. Jaylee, do you want to work with Esmeralda and Pamela? Brenna, do you want to chat with Evan? I mean, I know you guys are working on stuff, so when you're ready to. Evan, is it clear to you I'm saying if nucleophile attacks here, if nucleophile attacks here, 2 different times? Is it clear to you that what mechanism applies to attacking at what place?
No.
If the nucleophile attacks here, this is what it looks like.
Oh, I see what you're saying.
If the nucleophile attacks here, this is what it looks like.
Gotcha.
And we showed all of the resonance forms here because none of them were minor. They were all the same placement. We only showed 2 here, and we ignored the 3 that placed the negative charge on carbon because that's more minor than placing the negative charge on oxygen.
Gotcha.
It doesn't actually minimize the number of resonance forms, but it maximizes major resonance forms.
Gotcha. products too?
Yes and no. Actually, the product on top, you notice they're just structural isomers. They substituted different chlorines.
Right.
The product on top is the major product because of this energy diagram.
Okay.
It is the easiest to access. The product on bottom is the minor product because in order to get enough energy to do this reaction,
Yeah.
you have already had far and away more energy to run this mechanism.
Right. You would have just gone straight over that hill before you.
Exactly.
Okay.
By the time you get the energy to do this, you've already gone over that hill.
And then what about the green?
The green is, suppose we want to try and substitute this chlorine now, or substitute this chlorine. The fact that we have an electron donating group, the ether, NAS is prohibited. And I say prohibited instead of inhibited because it's basically impossible to get over that activation barrier. It is inhibition, but it's such an extreme inhibition. Students think inhibition means like, oh, it's harder now. Yeah, it's like impossible.
Right.
That's the idea. What drew you, usually the ends of the spectrum are the easiest to determine. What drew you to the ends of the spectrum? And meta is not as effective at pulling out electron density. Okay. What about the other end of the spectrum? So the amount of electron withdrawing groups and the placement of electron withdrawing groups. Nice. And what did you say about this one with the OH? Is that an electron withdrawing group? Do you agree? Pamela, do you agree? To be an electron withdrawing group, you notice how our electron withdrawing groups always have a pi bond in them? Does OH have a pi bond in it? It doesn't. And notice how I circled up there the ether has a lone pair. That makes it an electron donating group. Does OH have a lone pair? Absolutely. So OH is an electron donating group, which means, notice in blue, our electron withdrawing groups are only meta, and the energy for blue is like right there in the middle. But then at the end, we got those products that have an electron donating group, and now the energy in green is off the chart. Placement of an electron withdrawing group is one thing, but the presence of an electron donating group is another. So I would rethink your 3 and 4. But I want you to feel confident on it, so I'm going to call on you guys to rationalize that. You're doing great.
Would this one be,
I can't give you answers, I'm sorry. I just work here.
would that one be the least because it's electron donating group?
I like that reasoning, yeah.
Okay. And then this one, meta electron withdrawing group, so that's
That's not meta.
para. Oh. Okay, yeah, meta's the 1, 3. Para's 1.
Good,
4.
good. You got to know your 1, 2, 1, 3, 1, 4s.
So this is. Okay, so this one though would be. Wait, meta, and that one would be. Not good.
Well, I mean, it's not that it's not good. The presence of the electron withdrawing group still pulls electron density away from the ring, still makes the ring a better electrophile, but it doesn't contribute to resonance. If something is ortho or para, it will contribute to resonance.
Okay.
You also might want to help,
Help!
because it is
I need
ortho,
somebody help.
right?
What?
Is ortho or para one more stable?
No,
Okay.
no. I mean, look at this. One of the resonance forms
Well,
has an
I
electron
said
withdrawing group
no.
ortho.
Jude said it was.
One of the electron withdrawing groups is para.
Right.
Neither of them exist, right? Because
Right.
it's resonance, so it doesn't matter. Maybe you're thinking like sterics. If I have a group that's ortho, does it create more steric strain and make it harder for the nucleophile to attack? Don't worry about it. We won't worry so much on that. But it's actually really convoluted whether ortho or para really increases the energy or decreases it. It's more than just sterics. Electronics plays a big role in it.
So we were ranking these. And then if that's orthopara
Mm.
on bromine, that's also orthopara.
Those groups couldn't be more different.
They're the same.
So looking at the OH and looking at the nitrile
Right.
should not be a wager of one is ortho, one is para. That it should be night and day.
No, we're just like ranking on the reactivity because they're both orthopara. Are they on the same level of reactivity?
Not even close.
No.
No, they're more like red to green.
Okay.
And you have to rationalize why. Which one is red and which one is green.
I think it's
Do you
because
oh yeah, tell me.
you can't, if you move this bond up, it's gonna, what's it called, like break the octet.
Break the octet. OH, what Jordan's saying is OH is not an electron withdrawing group.
Even though it's ortho.
Yeah, it doesn't matter its position, it matters its identity.
Okay.
If it's not an ortho-para group, I'm sorry. If it's not an electron withdrawing group,
Okay, then it's bad.
it's what?
Donating?
Right, just like the ether in our final product was an electron donating group because it had lone pairs right off of the atom, right off the ring. OH also has lone pairs right off the ring. And what do electron donating groups do to NAS? They skyrocket the activation energy. They prohibit NAS.
So, then, between these two, because this one also won't.
It won't contribute to resonance, but does it push electron density in?
No.
Is that a donating group?
No.
No, it's not. We looked at that the other day.
So then, it'd be like that. Because this is
Now you're going to have to convince them. Brenna, you're still getting the mechanisms? Okay. How far are you? On the bottom one?
I'm on the bottom one.
Okay. Did you get this image on the right too? The energy diagram? Okay.
Yeah. Like the whole thing, or why this one doesn't. This one won't donate, or it won't. Yes, because
You got a question, Evan?
if you
So
do this, like let's say
I'm working on
move
it.
that
So
one
it's like,
or whatever.
so the sigma complex,
That can't.
what does that mean?
You have to move
Yeah, we discussed that last class, that the sigma complex is this little guy where you break aromaticity and then reform aromaticity. And I'm not sure why they named it sigma complex, but my thinking is it's a resonance set where all of the sigma bonds stay the same. That's true of all resonance.
Yeah.
Every resonance form has the same sigma complex, the same sigma bonding, and only differs by placement of pi electrons. So I think they took this name that is true of all resonance forms, and I think they applied it to the resonance intermediate in these aromatic substitution reactions. I don't actually know why they name it that. It's not a terrible name for it, but it is a little weird.
Gotcha. So, I mean, I heard you kind of telling them it's like it matters, you know, for each one there's going to be ortho and para potentially, you know, so it matters whether it's going to be like the red one or the blue one, sort of, so to speak. So, like for example, these are ortho and then
Because that's
para.
what that's showing.
So,
The
would
first
this
one
be
is that it's meta.
more
Or
reactive
the
because
blue one, sorry. And
these
since it's meta,
groups
it
are
never
going to be
goes
ortho
into
and they
that
just have to go like right over to the
So
electron
that's where I'm
withdrawing
a
group?
little bit confused.
Yeah. The fact that the electron withdrawing group is ortho or para. No. Sorry. Are you asking, is the ortho electron withdrawing group more significant than the para? Because both are equally significant.
Yeah, no, I was saying more in general, like since they're equally significant.
Like this group that's ortho to the leaving group versus this group that's para, they play as big a role as each other.
Right. I guess my question more was this molecule compared to the other ones would be more reactive since the electron withdrawing group is ortho and para.
Mm-hmm.
Compared to something like this, which would be meta.
Right.
But why can't this one? Oh, because it's.
Okay, are you guys ready?
Yeah.
What I want to try and synthesize is the key features you had to look for to rank these. And I have an idea in my head of how to say this, but I want to see if you guys can figure it out. So, Brenna, you're okay if I erase this left side? Okay. What was your ranking? Can you name, IUPAC name, the most reactive structure? You were looking at them, but you weren't thinking about their names. That's a good start, but that doesn't give us locants. Yeah, structural isomerism. Good. 2-bromo, 1,3,4, 1,3,5 trinitro benzene. 1,3,5. That was the most reactive. Why do you think that's the most reactive to NAS? It has the most resonance structures. And it has the most resonance forms because it has the most electron withdrawing groups. Okay, what was the second most reactive? Can you name it? Do you remember how we name a nitrile, a CN group in the prefix? No, that's if it's NH2 coming off. NH2 is aniline, but CN is just a nitrile, a cyano group. So here we have 1-bromo, 4-cyano, or para-bromo-cyano-benzene. Para-bromo-cyano. And this took second place over meta-bromosulfonyl benzene. Why? placement. Same number of electron withdrawing groups, but the placement of the electron withdrawing groups. And our least reactive. Can you name it? Good start. Orthobromohydroxybenzene, orthobromophenol. I have seen somebody call it benzenol. I don't like that name. I've seen one person name it that. I've not seen anybody else name it that. Orthobromophenol. Why is this our least reactive? Tell me. It has an electron donating group, which we said skyrockets the activation energy. Maybe not impossible, but just not feasible. So the reactivity depends on, you guys hit on each of these in your ranking. The reactivity depends on the type of group present. Does it have electron withdrawing? Does it have electron donating? The placement of the groups. Are the groups orthopara to the leaving group, or are the groups meta? And the number of groups. Do I have one electron withdrawing group para, or do I have 3 electron withdrawing groups, ortho, para, and ortho? All of these things contribute.
Would it be accurate to say that, well, because I'm just confused on like how you would determine if something's withdrawing or donating?
We'll talk about that actually today. Yeah, I should have given a better example of that. All right, now I want you guys to consider where these two structures might fall into the sequence that you've already created. By the way, we're going to be talking about EAS soon, which is different than NAS. So I will always clarify reactivity rankings by what type of reaction we're ranking. They are exact opposites of each other. So ranking one would give you the exact opposite order of ranking the other. Talk to me about bromobenzene. Where would you anticipate bromobenzene would fall into this sequence?
Either like the most or the least.
The most or the least. I feel like that's not a great place to put bromobenzene, on one side or the other. And the reason I say that is it's hard to get more electron withdrawing groups on this structure. There are 2 more that we could place, but it's hard to do that. And electron withdrawing groups decrease our activation energy. So with no electron withdrawing groups, this cannot be more reactive than having 3 electron withdrawing groups all in the right positions for resonance. So I don't think it can be more reactive. And I don't think it can be less reactive than this, which has an electron donating group. And that's going to increase the activation. So it's got to be somewhere in the middle. but I want you to think about what makes it hard to know exactly where it goes. Jaylee, you have a thought? I would say you should be thinking that it might be more reactive than this or less reactive than this with the meta group. Because this doesn't have an electron withdrawing group at all. And the electron withdrawing groups pull electron density away from the ring, making it easier for a nucleophile to attack. So with no electron withdrawing group, this is probably less electrophilic. Yeah, it's a shame that this is meta, but at least it has an electron withdrawing group. You agree? So with that in mind, how do you think bromobenzene falls relative to meta-bromosulfonyl benzene? Less reactive, because it has no electron withdrawing group at all. All right, what about 1-bromo to nitro-3-sulfonyl benzene? Can you use similar logic to try and place where this one belongs in the sequence? Tell me.
I think it's going to be 1.5.
1.5, the second most reactive. Tell me why.
Because it has an electron withdrawing group that it will use because it's ortho to bromo, but
One electron withdrawing group that will be in resonance,
yes, but the other one won't be because it's paired to the bromo.
one that won't be in resonance, but still more than one. So it has more than one electron withdrawing group, but one of its electron withdrawing groups isn't the most effective in the resonance. That doesn't ruin the effect of the electron withdrawing group, it just doesn't maximize the effect of the electron withdrawing group. So our second most reactive is the one with the second most electron withdrawing groups, even though not all of them are involved in resonance. Great. Type of group matters, the placement of the group matters, and the number of the groups that matter, not necessarily all in that order. All right, it's time to do some synthesis. So on the back side of your sheet, I want you guys to take the next 10 minutes to solve the, I'm saying 10 minutes, I actually feel like you can do it in 5. To do the first 4 problems on the top. Fill in the reagents on the left that are needed, and fill in the products on the right that are formed. After we solve those together, we'll talk about the synthesis as well. Was this energy diagram helpful in understanding reactivity? Somewhat? Could have been better? Yeah? Okay. We're going to be drawing a lot of them this semester, so I want to make sure you can understand them. And feel free to work together on solving these problems. Feel good? Feel free to start on the synthesis if you are done on the top. Oh, you're not done on the top. We haven't talked about this yet.
Okay.
That will come in our next set of reactions. Which means you don't need it, right? But this is not exactly the reagent that you think it is. Is there an octet on that nitrogen, the way you've drawn it, Justice?
No.
But the way that Evan's drawn it, he actually indicated a negative charge.
Yeah, it's negative.
And that's true. Good. So, I mean, we can assume lone pairs. But I do want you to know there are 2 lone pairs on that nitrogen. In order for it to have a negative charge, it must have 2 lone pairs. Lost carbon. Perfect. Great. You forgot your ring or your pi bonds. There you go. Great. You don't know what this is? Well, do the same thing that you did here and just do it to that guy.
Oh, okay.
Mm-hmm. This one's not done, right?
Yeah.
Okay, good. This is not wrong,
Do I need to add like
but it's not right. That works, yeah.
or NA?
Or a negative charge.
Negative charge, okay.
Either a cation or a negative charge. Perfect. Good work, Evan. That's it, Brenna. Great job. Can I see what you did for these two? Oh, you didn't have them yet. Okay. This is a good idea, having a counter ion, because we need a strong nucleophile, so it'll need to be negatively charged. Good start. Esmeralda, is that a covalent bond between sodium and oxygen and sodium and nitrogen?
This one?
Yeah. Is that a line, a covalent bond?
Yeah.
Is it not an ionic species? There you go. Sometimes I feel like I'm being like nitpicky,
No.
but you know the difference, right?
Yeah. No. Yeah.
Good.
But that makes
Because when you dissolve sugar in water, none of the bonds break, but when you dissolve salt in water, the ions dissociate. So there's a big difference. And I've seen it on mechanisms, and I have to take points off on mechanisms because you're assuming a covalent bond that doesn't exist. This is perfect.
Oh.
Yep. In fact, you could leave Na plus off. You don't have to, you can show it, but it's a spectator. It doesn't change the chemistry that actually happens at all. It's just gonna end up with the halide at the end anyways. Okay, good work. Great. Awesome, you guys are doing great. Now this is not an incorrect way to draw it, but there are a lot of ways for C2H6 to show up. And I want you to tell me what way do the 2 carbons and the 6 hydrogens show up? They show up as 2 sets of CH3. So saying CH3, 2, actually gives me more structural information than C2H6. Great. You could always just erase this and draw a negative charge on the end. You could draw it, right? Draw the structure, totally. Okay, and this one's great. And did you get these yet? So close, but you lost your H on the end. Do you see how your nitrogen only has 2 bonds? Good. Nitrogen likes 3. It came with 2, and both of those groups should be there. Good.
So I need just
That's it. Yep.
Thinking about that.
Mm-hmm. It's not a bad idea to think through the mechanism,
Yeah,
but I want you to be able to make that jump quickly as well.
sure.
This is not exactly correct because it's not a strong nucleophile. That is a weak nucleophile.
Oh. Would it be
It would. That'd be great.
okay.
This is also not exactly correct. Do you know why?
Why? Oh.
Your aromatic ring is a cyclohexane. There you go.
So wait, this, you said this pH is a weak nucleophile?
No, the way that he drew it,
I drew it with a OH.
he drew it as an alcohol and not as an alkoxide. Okay, are we ready to talk about these answers?
Yeah, we're just talking about.
The next ones? Good, good. All right, so on the top, what I saw a lot of you guys do was just recognize what's drawn on the ring, erase the ring, and add that as your nucleophile. And there's different ways that you can show this. You could show this as NCH3 2 minus, but it needs to be minus. It needs to be a negatively charged nitrogen. It needs to be a strong nucleophile. You could have shown this as NaN with the two methyl groups coming off, or you could swap that Na for K. Those are all equally perfect answers. Any combination of bond line or condensed form, all of them work perfect. What it needs to be, though, is a negatively charged nitrogen with those two methyl groups. Sometimes I'll see someone take the chemical formula of the two methyl groups or whatever the chain is, and they'll condense it into a molecular formula. But this really changes what I know about it. I don't know anymore whether this is two methyl groups or whether there's some structural isomerism going on. So I want to see the structure that's needed. Same thing on the bottom, just lob off this group and introduce the nucleophile. And again, you could show this with a counter ion. You could take that pH and you could draw it out as a benzene ring. All of these are accurate. But submitting this is not the same, because there's a covalent bond between O and H rather than the ionic bond between oxygen and sodium, oxygen, potassium, or just showing that negatively charged. This is a weak nucleophile, whereas these are strong nucleophiles. And for that same reason up here, this would be a bad answer because it gives us a weak nucleophile. Okay. Then on the right, it looked like a lot of you got this pretty easily. And again, there's just so many different ways that you can draw these answers. I want you guys to be comfortable with that. I want you to feel comfortable knowing that there's different ways to interpret the same molecule. Not one is necessarily better than the other. And on the bottom, I do want to point out, however, something that I mentioned last week, which was a mono-substituted benzene ring can be abbreviated as pH, which is why I gave you the structure of bromobenzene, but I drew it on the board as PHBr. Perfectly acceptable. But a di-tri-poly-substituted benzene cannot be abbreviated as pH because the structural relationship has to be explicitly shown. Thank you. The leaving group? Did I miss any others? Good catch. Okay. Synthesis. These next 3 problems must involve more than one step. I want to take you guys through the first one because I do feel like there is an answer that makes sense to most of you that I honestly expect I would see. That you would approach this and say, can't this be done in one step? Start with bromobenzene, and I end up with 2-bromoethoxybenzene. All of that has to be set in parentheses. 2-bromoethoxybenzene. And I think most students would see this question for the first time and say, I have an oxygen nucleophile that needs to substitute the benzene on the ring, so I'll just do exactly what we did in these other problems, and I'll introduce whatever group I need off of the oxygen. The problem is in trying to keep this reagent. If you produced this reagent, it would just react with another equivalence of itself and polymerize. Not ideal. It's hard to use a reagent that is reactive to itself. Strong nucleophile from OChem1, good leaving group from OChem1. It just does SN2 across multiple equivalences, can create a polymer chain eventually. I'm going to have to do this in multiple steps. And this is where critical thinking and creative thinking start to blend. You need to think critically about what the reagent you're providing is actually capable of doing. It's capable of reacting with itself. And you need to think creatively about getting around that. Maybe I don't add the bromine right away. Maybe the bromine is something that comes later. So when I encourage you to do synthesis, one of my tips is work forward and backwards. Well, my forward step was to do it all in one step and use this guy, and that's out the window. So what I'm going to try and do now is work backwards. And my idea here to work backwards is to see if I can put that bromine on after the NAS step has already happened. So I want to see if I can have my oxygen on and then have something connected to the oxygen that would allow me to add the bromine where it is. And I'm thinking, have an alkene. If I have an alkene, I could run an HX addition reaction or a halohydrin addition reaction. I could try to, a radical halogenation reaction. I could try and get that bromine on using an OChem1 reaction. And if I can do that, then I can work forwards again to say my nucleophile is this negatively charged oxygen, a vinyl oxygen, an oxygen that has this group attached to it. Now, I'm not going to lie, in solving this in front of you, I'm seeing more problems with this than I intended, and I should have not done a vinyl halide. I should have done an allyl halide. So I'm going to be honest. If this were a better problem, the structure would have looked like this instead. It would have had an extra bromine. I don't know if you guys want to make that change or just follow my logic. There's some chemistry to it that we're going to talk about at the end of the semester. The difference is whether the oxygen is actually connected to the alkene or not. And a better synthesis here would have not had the oxygen connected to the alkene. Okay, if you want to know why, it's because there's a resonance form here that puts the negative charge on the carbon, and the carbon is a better nucleophile than the oxygen, so the oxygen would not be likely to attack. So that was not the structure I should have had. Okay, so oxygen as a strong nucleophile substitutes the bromine, and now this alkene can go through anti-Markovnikov HX addition. It needs to be anti-Markovnikov because I want the bromine on the less substituted carbon, the hydrogen on the more substituted carbon. If I did HX addition, my positive charge would end up more substituted, and so would my bromine. But I don't want my bromine more substituted. So radical HX addition. Fun. That is a challenging one in my opinion, but it highlights some of the limitations. You can't just have whatever group you want. There are some groups that just don't work well. Okay, you've got two other synthesis problems. Why don't you take the next 10 minutes to work through them as best you can. These are both two-step syntheses, by the way. One intermediate, two sets of arrows. Man, those rings showed up really big.
Which one goes first?
I feel like we should change the other leading first.
Mm-hmm.
And then after that?
You're welcome. You're welcome. Jordan, I didn't add this to Canvas. Can you remind me at the end of class, because I'm worried that if I try to open Chrome right now, my recording's going to crash. Thank you. Don't you just love a little mix-up first thing in the morning?
I'm just trying to figure out what's going to make this carbonyl.
One of my other tips in synthesis is map your carbons or count your carbons. Keep track of what carbons are added, what carbons are lost.
on how to get this to a carbo acid. Maybe make it into alkene.
This thing.
Ooh, Jordan found it. Actually, Drew, you're not on a bad track there. But with the alkene possible, so you could radical halogenation onto that benzylic position, and then you could use tert butoxide and make an alkene. But then if you did any type of oxidative cleavage, you'd make a ketone. And then there are things we can do with ketones, but it would be you'd have to do Wolff-Kishner or Clemmensen reduction of the ketone to make it an ethyl group, and then you'd have to radical halogenate again, and then you'd have to do another elimination, and then when you cleaved it, you could do oxidative ozonolysis to get a carboxylic acid, or just use Jordan's methods.
Yes.
With alkenes, right? Looking at alkene reactions? Good, good. Don't forget, we've got that handout from the first week that has all of our alkene reactions as well. Good. That's the resource, that's the type of resource I want you to have.
Starting over.
What was in your brainstorm?
I was trying to do oxidative at first, just
To get rid of
to get rid of
one carbon
one carbon,
and turn the other carbon into
the other.
the aldehyde.
Yeah,
So which of these reagents were you going to use?
I was using this one.
Well, that looks like exactly what we needed.
Oh,
So why not?
because you were talking about oxidative cleavage and having it go through all the other.
Yeah, but I was talking about this one.
Oh, okay.
Got to be careful. You got to be careful not to overhear other people's conversations and second guess yourself. Brenna had the solution. She had it right. And then she thought maybe she misheard.
We did it as that. We're gonna change that first so that it becomes a better
Okay, so my
thing, and then.
only concern there, and also what's this?
Oh.
Okay, it didn't come through it. Oh, but yeah, good. OH minus. My concern there is making a carboxylic acid and then introducing a strong base. You're just going to get acid-base chemistry. You've got a proton donor and a proton acceptor,
Yeah.
and the easiest reaction, remember that diagram I had before and red was really low? This would look just like a flat line. The easiest reaction is acid-base. So I agree with you, it would make sense because it has that carbonyl, but it's not like the ketone or the aldehyde. It also has a proton that it can donate.
So this one is also? Or
Not
this one?
acidic.
Okay.
That H bonded to the aldehyde is not acidic, but the H bonded to the OH of carboxylic acid, very acidic. About 10 million times more acidic than an alcohol. Right. So this is a good route, but I fear it addresses what I just said to them, which is that you get this strong base and a good acid, and that instead of seeing a nucleophilic substitution occur, you'll see just acid-base chemistry occur instead. I think that would work, yep. We said that the alkyl groups allow NAS, so we can still do it. And this is perfect. That's great. What are you thinking? I like that first step. In fact, this one's not wrong either, but those two steps could be flipped. And the difference would be that the NAS would happen quicker because we'd be creating an electron withdrawing group.
Oh, okay, I see.
So Evan, you got the right idea, but you did miss something in your product. Yes. It's those small things. When I started tutoring, I'd come over and catch people doing little mistakes like that, just for getting an O. And they'd go, how can you see all of that? You've looked at my paper for 5 seconds and you noticed those errors? Yeah, that's like, that's what happens when you do it day in and day out.
Does KOH work?
Absolutely.
Okay.
All right, I want to talk to you guys about the solutions here. So for our first one, a lot of you guys figured this out. I need to cleave a carbon. Actually, I'll number this the opposite way so that it looks more sense. If I'm mapping my carbons, it should be obvious that I need to cleave carbon number 3. So I need to do oxidative cleavage, an alkene reaction. So I'm going to start with O3 and DMS, or zinc, which gets me from parabromostyrene to parabromobenzaldehyde. And now I have an electron withdrawing group that is para to my leaving group. So when I do NAS with sodium hydroxide or potassium hydroxide or hydroxide, it's actually easier. I could have swapped these, and I could have done the NAS first and then done oxidative cleavage, but the NAS is going to be so much faster with that electron withdrawing group already in it. Now with this one, I saw a lot of you solve it by using that benzylic reaction we learned. Chromic acid creates benzoic acid. We go from orthochloroisopropyl benzene to orthochlorobenzoic acid. And then NAS with sodium dimethylamide or potassium dimethylamide or just dimethylamide. The problem is we've created a good acid in the presence of a very strong base, which means this reaction is never actually going to give us the NAS that we want. It's just going to give us a negative charge here. So despite the fact that the electron withdrawing group looked really appealing to do at first, it shouldn't be our first step. We're going to need to do NAS first. And we said that alkyl groups allow for NAS to occur. So the isopropyl is not helping. It's not making this NAS quicker or lower energy, but it's not hurting. And then we can do oxidation. Now, I'll be honest, if this were a graded question, I would give lots of partial credit for this synthesis, because the intermediates that you drew make sense based on the reagents you provided. The reactions you showed were plausible. But the route had that plausible issue at the acid-base versus nucleophilic step. Lots of partial points for that problem. All right, so I just handed out this next packet that we will spend the rest of the week going over. And you'll notice that it's on the equal but opposite type of aromatic substitution, electrophilic aromatic substitution. And I want you guys to tell me briefly, what role does the ring play in electrophilic aromatic substitution? remember that in NAS, well, you tell me, what role does the ring play in NAS reactions? Is it nucleophile or electrophile? The ring is the electrophile, which is why we wanted groups that would pull electron density away from the ring so that the ring was hungrier for electrons. Now with EAS, what role does the ring play? Is the ring nucleophile or electrophile? Nucleophile. That's why we say it's electrophilic aromatic substitution. We substitute the aromatic ring with an electrophile. So the ring must be the nucleophile. And things that make the ring a better nucleophile are things that give electron density to the ring. Give electrons for the ring to use, electron donating groups. I want to point out that NAS required the substitution of an aryl halide. If there wasn't an aryl halide, there was no substitution. EAS removes a hydrogen always, no matter what. EAS takes a hydrogen off of the structure. Equal and opposite reactions. Notice that the sigma complex had a negative charge in NAS. The sigma complex has a positive charge in EAS. The ring was attacked in NAS. The ring does the attacking in EAS. Stabilized, or in other words, activated by ortho-para electron withdrawing groups in NAS. Now stabilized, or in other words, activated by ortho-para electron donating groups. Equal but opposite reactions. Stabilization always comes from resonance. Resonance always involves ortho-para groups. But the opposite is that the groups are electron withdrawers or electron donators. The opposite is that the charge in the resonance is negative versus positive. The opposite is that the ring gets attacked or the ring does attacking. They are equal but opposite reactions. Is that agreeable? Equal but opposite? Which means that it can be really easy to get confused between them. However, EAS has 6 named reactions that we're going to go through, whereas NAS didn't have any names. NAS involved nitrogen nucleophiles or oxygen nucleophiles. That was it. NAS was as simple as a negatively charged nitrogen or a negatively charged oxygen. EAS has these 6 variations that we're going to see. And we're going to spend more time on that tomorrow. But I want to spend the rest of my 3 minutes introducing those electron withdrawing and electron donating groups in more detail. So you'll notice at the top are my electron donating groups. And I do agree, I did this poorly. I should have put EDG, X, EWG. What can you do? So our top structure demonstrates some electron donating groups, EDGs. And the distinction that we see here, alkyl groups simply have electron density that they can push towards the ring. Or that can be a place of a tertiary carbocation intermediate. That's a stabilizing part to resonance, is having a more substituted carbocation. Whereas nitrogen groups have a lone pair that can be donated in, and oxygen groups have a lone pair that can be donated in. So alkyl groups are considered weak electron donators. Oxygen and nitrogen are strong electron donators. And I want you guys to think about what is the strongest electron donating group. Then we have halogens. And halogens are strange because they have a very strong dipole that pulls away from the ring, feels electron withdrawing, but they have lone pairs like the oxygen and the nitrogen that can be donated into the ring. So they are neither like the electron donating groups, nor are they like the electron withdrawing groups. Halogens are a group of their own. And then we have our electron withdrawing groups. And the groups I want you to be familiar with as being electron withdrawing groups, that's the nitro group, which we've already spent some time looking at. The nitrile group, we had an NAS mechanism with each of these electron withdrawing groups already. And then I'm putting a carbonyl, and I'm not saying whether that carbonyl is a carboxylic acid, an aldehyde, a ketone, an ester, an amide, just the fact that it has a CO double bond. What each of these groups has in common is the ability to pull electrons in from the ring towards their more electronegative atoms. They're each pulling electron density out of the ring. I'm sorry, those arrows are not good. They were going to be bad arrows anyways, because I was going to have to double up on bonds. So they're just kind of showing in general electron density leaving the ring. Okay. Tomorrow, we will talk about details for these reactions. We're going to go through 4 of the 6 mechanisms. And then we're going to talk about directing effects and activating effects, which is almost exactly what we've written on the board here. So, see you guys tomorrow. Enjoy the rest of your day. And keep working on your active homework. And your written work. You have more written work that you can tackle now, too. Okay, see you guys tomorrow.